Right, so I thought I'd take a picture of it as it stands at the moment, but I'm planning to get rid of this upper left section because it doesn't really work converting binary into decimal numbers, and I need the space more than I need the output in decimal. So I did manage to get most of the control signals in for the second EPROM, so these all now go over to the left hand side of the breadboard base. It does the memory, and this is the logic unit, and all the controls for the logic unit are there. There is a problem with this in that it won't do two at a time. So another reason for getting rid of this is here underneath this mess of wires is my flags chip, and I need to have more room for the flags because I'm making a change to the zero flag and the overflow. So I've removed that now, and my plan is to put in a set of logic gate functions. So the idea here is that I have a couple of OR gates and an inverter that create a zero flag. So I need room to put these chips in. So I've expanded the whole board, which you're looking at it a bit upside down now, but I've put in the timer so that the timer will now move to all the chips. All of the chips need a clock cycle, so the clock is there near the red thing I'm pointing at, and I'll need to run a completely new set of control signals for everything, for all the EPROMs and the clock signal. And the EPROMs will have a different clock signal from everything else. The multiplexers and the inverters that I'm using with those all make the signals high to enable them, although some of the chips, like these logic unit chips, are enabled low, so that's why they go through the inverter to change it. So now that I've put these in place, I can continue to put more control signals in for the clock, and the remainder of the flags still need to go in. So the A and B operand switches still work, but I need to add them in here. So I've got a new breadboard, empty, ready for spare. I've got this one that I've cleared off now that I can use for additional flags. So I've got space up here for more logic gates to do the flag for the overflow, which is going to take a lot, and I've shifted all that from underneath that mess of wires up to there. But the overflow flag is going to take a lot more logic chips, and so I'll probably wind up using the rest of this particular breadboard for that. And then I need to run those controls down to the EPROMs. So the adder now works as I've expected or planned, so that all of the inputs or the output of the adder goes into the OR gate. If they're all zeros, then it should be zero. However, if it's all zeros and the carry flag is set, that means that actually it's not zero, it's just rolled over one, bit like your mileage. So that's what the second OR gate is doing in combination with the carry flag. But if all of those are zero, then that means there's a zero flag. But because I need the zero flag to be positive, I put it through an OR gate so that the signal is high rather than low. So it sets the zero flag in the latch. The zero flag is probably the most used because it's for branch on equal, branch on not equal, all the comparisons. They're all basically doing subtraction from zero and to see if it's zero. So if you're subtracting register A from register B and it's zero, then they're equal to each other. So a lot of that is needed for the assembly programs that I'm doing next, or in the process of doing. The other thing I need to do is put the other flags in. The overflow, carry in, carry out are already there. the zero flag I've now done, and the overflow flag will be probably the most difficult one to do. I still need to decide whether I'm going to have multiple XORs. It probably would have been better in this logic unit to have it not what I'm doing now, which is enabling one side, the A side or the B side, but rather enable both of them always, and then switch between A or B, or allow both to be put into that latch. At the moment they all go into that latch that I'm pointing to there, and it's either A or B. But what I really should do is put a second latch in for A and a latch for B, so that I can do both at the same time. But I don't know if I'm going to do that, or if I'll just continue to support one operand logic. The other thing, I want to move the memory. So this is the memory address register, it sets the memory, but I want to add memory into the A and B operands. I need that so that I can operate on the memory as a constant. So run add 1 to register B, A1 for example, or to add register 1 to 32. So I can also use these registers as a scratch register for subtraction, because when you do subtraction you need to store the knotted value somewhere temporarily, and then put the knotted value and the 1 into the adder. So what I've been doing here is I've been writing out for each of the commands I plan to support how much microcode it's going to take to do it. Now I've got 7 clock cycles I can use for each instruction set, but the first 2 are always the same, and then that leaves me with 5 instructions or byte codes I can use for the remainder of the instruction. Some of the instructions you can do them all at the same time because they don't conflict with each other, but some you need to wait for the next clock cycle to take a result, for example. So one of them may have one set of commands, so I can assert, and then latch, all in the same byte operation. But some need multiple byte operations. Subtraction is a good example of that. So the 2 that you always need is timer, the 7 clock cycles I get. So timer 0 and 1. The first one is always put the program counter into the memory address register, which loads the instruction at that point, and then move from the memory address register into the instruction register, and then increment the program counter probably at that time. So those 2 instructions have to happen every time regardless, because you don't know what the next instruction is. So those 2 always have to happen. There's no way to not do that. And then you get the remaining 5 clock cycles to complete those instructions. So I've been trying to work out to make sure that all of the opcodes are distinct, in that they don't need, they are one cycle of the clock cycle. When I was doing the software, I had erroneously combined things that would take 2 clock cycles into one command. That won't work, obviously. So I've done most of the work here. I don't think I need to expand much more than this. I'm probably going to wind up using all of this, and most of the control signals are in place now. I've got some places where you can, what I'm showing you here, where it will show the data that's in either the data bus or the adders. I don't think I need a digital transformation, which is why I got rid of that other thing. And I just need now to wire up the memory addresses. I need to wire the memory results into the A and B operand, and I need to be able to latch the memory and use them as a scratch register, as it were. The flags is now out where I can get to it, and I can reset those. I'm probably going to wind up putting another latch somewhere in that mess of yellow wires, but I don't know how I'm going to fit it in at the moment. So here's the software, and this is the original C program that I was using, and I've put a lot more information into the switch in the instruction builder, and I had to change a significant amount of these opcodes because of the mistake I was making in my thinking. Having combined opcodes, I need each opcode to be distinct and executable in one single clock cycle. So to load memory address, for example, has to be one argument into the EPROMs. Now obviously I can mask out a lot, and some of them it can do simultaneously. So not this one, but for example the move just above it, move from one register to another can be done instantaneously in a single cycle. You don't need to have more than one. You would need the three opcodes: the load instruction, load memory address, return the memory address, and then run the instruction. So that's it. So I've been looking at doing an assembler in Rust, and what I've got here is I'm at the point where it can read a simple assembly language file and lex the values for the instructions. So as you can see here, it's gone through and lexing out the important bits in that file. So I'm doing this all in Rust rather than C, mostly as a learning exercise to learn or get better at Rust. So it's pretty straightforward. It's just lexing the values, and then I'll be calling, at the moment I'm only calling print statements, but I'll be calling the function that constructs the actual machine code for that instruction. But this is just tokenization and lexing the file, and it's it doesn't do in nested comments or anything really esoteric. It expects things to be well formed, so it's not extremely robust, but since I'm the only person writing it, I'll know the restrictions. This is the command set that I'm going to support. The commented ones I'm not going to bother with, the add carry and subtract carry, but these others I'll do. I think there's basically 22 commands here, and they take either registers or immediate values as an argument or a memory location. So that's pretty much it. I mean, it's a really simple language. I'm not doing anything difficult or esoteric. I'm not supporting a lot of the opcodes. I'm right now working on the structures to save the data. So the label, for example, is just where does it jump to. So I need to know where that memory location is for it to jump to if it branches back to the label. But I need to construct the instructions, the machine code based on the instructions, and so I need to define the data structures that I'm going to hold all this in before I write the function that spits it out. I may not even need that, because I can just write it directly from the function, because it's going to go through the file line by line, and assembly there's not a lot of jumping about. I'm not supporting things like origin. Everything is going to be at byte 0. It starts at byte 0 regardless. So I'm not doing anything like that. I'll probably load data first, so I will have a section, so I need to support that. So I'm at the moment it's mostly working with the lexing values and then trying to determine the data structures that'll be held, and then in theory just constructing the machine code is pretty straightforward because you just write it out to the binary file in order. So that bit will be a lot easier. And you probably can't see that, but I have actually got the code to write out the file. I just haven't, so I did a few tests to make sure I was doing it properly and that I got the right output, 16-bit values, but that's it.